Have you ever pondered over the laws of physics and wondered if anything could defy them? Welcome to the fascinating world where science meets the seemingly impossible, where the laws of physics, those fundamental principles that govern our universe, are put to the test. These laws, from gravity to electromagnetism, from thermodynamics to quantum mechanics, act as the rule book for the cosmos. Yet, there exist certain phenomena that, at first glance, seem to break these rules, to defy these laws we hold as universal truths. But don't be fooled. These are not violations, but rather intriguing puzzles waiting to be solved. They challenge our understanding, pushing us to think beyond the conventional, leading to deeper insights and richer knowledge. They remind us that science is a continually evolving field, always open to questions, always ready for exploration. So, are you ready to dive into these mind-boggling phenomena that seem to defy the laws of physics? Consider a concept that even Einstein referred to as spooky action at a distance. Yes, it's quantum entanglement. Dip your toes into the world of quantum physics, and you're bound to encounter phenomena that are, well, a bit mind-boggling. One such phenomenon is quantum entanglement. This concept, in its simplest form, is the idea that two particles can become so deeply linked that the state of one particle can instantly affect the state of the other, no matter how far apart they are. Imagine you have a pair of dice. You roll them, and no matter what, they always show the same number. Even if one die is in New York and the other is in London, if the New York die rolls a 6, the London die also rolls a 6. That's quantum entanglement, but with particles instead of dice. This is where things get a bit spooky. You see, in the world of quantum physics, particles don't have definite states until they're measured. They exist in a superposition of states, a sort of all possibilities at once scenario. But when you measure one of the entangled particles, it chooses a state, and its partner instantly chooses the corresponding state, no matter the distance between them. This seems to violate one of the fundamental rules of physics, that nothing can travel faster than the speed of light. Here, the information about the state of the particle seems to be traveling instantaneously, faster than light itself. But it's not actually about information traveling. It's about the inherent link between the particles, a connection that exists beyond our typical understanding of space and time. It's a concept that's both fascinating and perplexing. It's a concept that challenges our understanding of the universe, forcing us to rethink and redefine our notions of reality. So while it appears to defy the laws of physics as we know them, quantum entanglement is a fundamental aspect of quantum mechanics. It's a concept that's not just theoretical, but has practical applications too, from quantum computing to quantum communication. It's one of those things that, despite seeming impossible, is a very real part of our universe. Next on our list is the elusive dark matter, a concept that continues to baffle scientists. In the vast expanse of the cosmos, there exists a substance quite unlike anything we're familiar with. This substance, known as dark matter, is particularly peculiar because we can't see it, we can't feel it, and we can't detect it directly using any of our current scientific instruments. You might ask, if we can't see or detect it, how do we even know it exists? That's a great question. The answer lies in the gravitational effects we observe in the universe. You see, galaxies spin at such high speeds that the gravity generated by their visible matter alone wouldn't be enough to hold them together. They should be tearing themselves apart, but they don't. Something unseen is exerting additional gravitational pull, keeping these spinning galaxies intact. And that something is what we call dark matter. This invisible, undetectable substance is thought to make up approximately 85% of the matter in the universe. Let that sink in for a moment. The stars, planets, galaxies, you, me, and everything else we can see or touch only make up a meager 15% of the total matter in the universe. But here's where things get really interesting. This dark matter appears to defy our current understanding of detectable matter. According to the laws of physics as we know them, matter should interact with light. It should absorb light, emit light, or cause light to bend. But dark matter does none of these things. It doesn't interact with light or any other form of electromagnetic radiation, which is why it's completely invisible and undetectable. This is a prime example of how the universe continues to surprise us, revealing phenomena that challenge our preconceived notions. Dark matter, with its invisibility cloak and its refusal to interact with light, is a stark reminder that there's so much more to the universe than what meets the eye. it's still a mystery that challenges our current understanding of the laws of physics. Have you ever heard of the Mpemba effect? It's a phenomenon that seems to turn our understanding of thermodynamics upside down. In essence, the Mpemba effect is a paradoxical observation where hot water under certain conditions freezes faster than cold water. Yes, you heard it right. This seemingly impossible occurrence was named after Mpemba, a Tanzanian high school student who noticed this peculiar event during a cooking experiment. So how does this happen? Well, truth be told, despite numerous attempts, scientists haven't been able to reach a definitive explanation. However, several theories have been proposed to unravel this mystery. One such theory suggests that hot water evaporates more quickly, which reduces the amount of water that needs to freeze. The reduced volume then freezes faster than a larger amount of cold water would. Another theory is based on the idea of supercooling. It posits that cold water can remain liquid even below its freezing point, while hot water might freeze as soon as it reaches 0 degrees Celsius. A more recent hypothesis involves the concept of hydrogen bonding. Water molecules are bound together by hydrogen bonds, which are affected by temperature. As the temperature of water decreases, these bonds change, affecting the rate at which water freezes. Therefore, it's possible that hotter water could affect these bonds in a way that allows it to freeze more quickly. Yet another theory proposes that the convection currents in hot water help distribute the cold from the surface throughout the entirety of the water, helping it to freeze faster. However, it's important to note that these are all just theories. The Mpemba effect is not consistently reproducible, which makes it difficult for scientists to study and understand this puzzling phenomenon. It's one of those intriguing quirks of nature that continue to challenge our understanding of the physical world. This simple yet baffling effect makes us question our understanding of heat transfer. Last but not least, let's delve into the wave-particle duality, a cornerstone of quantum mechanics. Now, what's fascinating about this concept is that it defies the classical understanding of physics. In the quantum world, particles such as electrons and photons can exhibit characteristics of both particles and waves. Imagine tossing a stone into a pond. The stone, a particle, creates ripples that spread out across the water surface. These ripples are waves. In classical physics, the stone and the ripples are distinct. One is a particle, the other a wave. But in the quantum realm, things aren't so neatly divided. Particles like electrons and photons, the tiny bits that make up light, don't conform to this classical distinction. They can behave as particles located at a specific point in space at a certain time, but also as waves spread out over space and time, much like those ripples spreading on the pond. This wave-particle duality is evident in experiments such as the famous double-slit experiment. When light or electrons are fired at a barrier with two slits, we see an interference pattern on the other side, a behavior characteristic of waves. Yet, when we observe closely, we find that light and electrons arrive as individual particles. This duality is not just a theoretical curiosity. It's a fundamental aspect of the world at the smallest scales and has real-world implications. For example, it's the reason why we have technologies like lasers and electron microscopes, but it's also a concept that challenges our intuition. It seems to defy traditional physics, which treats waves and particles as separate entities. In the quantum world, they are two sides of the same coin, a coin that doesn't exist in our everyday experience. This is why quantum mechanics is both fascinating and confounding. It forces us to question our understanding of the universe, to accept that at its most fundamental level, reality is not as it appears. So, wave-particle duality, another quantum oddity, forces us to rethink our conventional understanding of physics. So, there we have it, 5 phenomena that seem to challenge our understanding of the laws of physics. We've delved into the mind-bending world of quantum entanglement, where particles are mysteriously linked no matter the distance. We've explored the elusive dark matter, an unseen force that makes up a significant portion of our universe. We've questioned the Mpemba effect, a curious phenomenon where hot water freezes faster than cold. And we've pondered the wave-particle duality, where light behaves as both a particle and a wave. These aren't violations of the laws of physics, but rather, they're intriguing puzzles that deepen our understanding and knowledge. They remind us that the universe is a complex and fascinating place, filled with mysteries waiting to be solved. Remember, in the world of physics, even the seemingly impossible can lead to groundbreaking discoveries. Until next time, keep questioning and exploring the universe around you.